Okay, so we're going to talk about some indifference formulas. But before we talk about those actual formulas, I have a question for you. Is a trig function, any trig function, does it hold to the distributive property? If I take this cosine function, and I could have taken any of the other 5, but if I take this cosine function and distribute it through the parentheses, would it be equal to the cosine of 75 degrees, which is the sum of those two angles? So some of you have your calculators out already, so great, make sure your calculator's in degree mode before you start punching anything in. I've already worked this out, and here's what I have found. I have found the cosine of 45 degrees is this 4-digit decimal. I have found that the cosine of, I have found that the cosine of 45 degrees is a 4-digit decimal, but this is its 4-digit decimal. I have found that the cosine of 30 degrees is this 4-digit decimal, and the cosine of 75 degrees is this 4-digit decimal. If I add the left side together, is it equal to this number on the right side? No, it's not. So here's the deal. This cosine function does not hold to the law of distribution, which means none of the trig functions are going to hold to the law of distribution, unfortunately, which is why we had to find a way around the distributive property for the trig functions, which is why the sum and difference formulas have actually been developed. So hang in there, and I'll get them up on here in just a moment. Okay, so let's look what these formulas look like. It looks like they're asking me to distribute cosine. Now notice, there's no inverse here, which means alpha and beta are both angles. So I'm trying to distribute cosine into 2 angles. Well, just watch a second, okay? There's a way that I remember these formulas, and yes, the more you use them, the more you remember them. But I've got my own little tricks to remembering them. So here's the thing. When I distribute this cosine, it's going to be the cosine of alpha times the cosine of beta. Got it? And then, just wait, don't write. And then I'm going to take the sine of alpha and the sine of beta. Now, I consider cosine a greedy function. Why? Because when we distributed cosine, I distributed the cosine first. So instead of it being an addition sign like it is here, it changes signs. It pays for its greediness, shall I say. If we were talking about distributing it over a subtraction, same thing. I'm going to take the cosine of both angles first. I'm going to take the sine of both angles last. And because this was subtraction, because cosine decided to go first twice, subtraction changes to addition between the two. Okay? So this is my way of remembering it. You guys are going to come up with your own. And like I said, the more you use them, the more you remember them. So let's talk about this sine function. Sine isn't greedy, so just watch. I'm going to take the sine of the first one and multiply it by the cosine of the second one. And then it gets to be flipped. Since I took the sine of alpha here, I'm going to take the cosine of alpha. Since I took the cosine of beta, I'm going to take the sine of beta. And since sine was not greedy, addition stays addition. Cool? Okay. Let's talk about if we subtract the two, same thing. Sine of alpha, cosine of beta. And over here, since I took the sine of alpha here, I'm going to take the cosine of alpha. Since this was cosine beta, I'm going to take sine beta. And since this was subtraction, it stays subtraction because cosine wasn't greedy. Got it? Okay, let's look at tangent. Now, the tangent almost looks like a distribution problem. Watch. Because it starts out with taking the tangent of alpha times the tangent, or plus the tangent of beta. So it looks like a distribution problem. Yeah, right. And then we get this lovely denominator. You're like, where'd that come from? I know, right? You can go look at the derivation of these things. And let me put up the tan of alpha minus beta. Again, it looks like a distribution because we do the tan of alpha minus the tan of beta. Yeah, and then it changes. The denominator is now 1 plus. The sign changes from the numerator to the denominator, just like it did over here. Cool? Okay, so hang in there. I've got some examples of us using these particular sum and difference formulas. Okay, so they're asking us to find the sine of 11 pi over 12. And they said to find the exact value. What does that mean? That's right, no calculator, so put them away. And you're like, well, how am I going to do this? Well, first off, let's ask ourselves, is 12 a typical denominator in radian mode? Remember, our typical angles that we have dealt with, on that 45, 45, 90 degree triangle, 45 degrees is pi over 4, isn't it? On our typical 30, 60, 90 degrees triangle, the 30 degrees is pi over 6. The 60 degrees is pi over 3, right? And on our unit circle, we have the 0 radians, and then pi over 2, and then pi, and 3 pi over 2, and then 2 pi. So we have pi over 2, shall I say, is another one. So here's the deal. Our typical denominators in radian measurement that we can find without a calculator are these 4 denominators. A 6, 4, 2, and a 3. Got it? This is a 12. This isn't going to work for us. I can't find this without using a calculator. But since they're saying find the exact value, that means don't use a calculator. So you're like, what am I supposed to do? If I could rewrite 11 pi over 12 into 2 different angle measurements, added or subtracted together, couldn't I use one of the sum and difference formulas for sine? Then that's what I'm going to do. And you're like, well, how do you do that? Here's my method. This is where my brain thinks. My brain's like, fine, 11 pi over 12. I know that's 1 pi over 12 plus 10 pi over 12, right? My brain works in addition mode, so I'm staying in addition mode. So that is 11 pi over 12, isn't it? This one reduces to 5 pi over 6. Well, that's good, because there's the denominator of 6. But this one doesn't reduce. It's still 1/12, and none of these denominators are 12. So this combination, though it adds to 11 pi over 12, isn't going to work for me because this angle is messing it up. Okay, so after 1 comes 2. So 2 pi over 12 plus what? Good, 9 pi over 12. That'll give me 11 pi over 12, won't it? Cool. Now here's what I'm noticing. 2 pi over 12 reduces what? Pi over 6. Yep, got a denominator 6. 9 pi over 12. It reduces, doesn't it? To what? Yeah, 3 over 4, right? Well, there's the denominator 4. So this is the combination I'm going to use. And yes, there's probably other combinations as well, okay? But I'm going to go with the method that works best for me, and this is what works best for me. So here's what I'm telling myself. Basically, I can rewrite the sine of 11 pi over 12 as the sine of this addition problem. Cool? And I know, because we just said it, that each of these angles reduces, right? That's good. And now you're like, okay, now I've got the sum of two angles. So you got to go use that sum formula, don't you? For addition, for sine, right? Okay, so hang in there a second. Let's see if we can walk ourselves through this. Remember, sine's not the greedy one. So I would take the sine of pi over 6 and multiply it by the cosine of 3 pi over 4. And then over here, since I took the sine of pi over 6, I'll take the cosine of pi over 6. Since I took cosine of 3 pi over 4, I'll multiply it by the sine of 3 pi over 4. Since sine is not greedy, and this is addition, this stays addition. Cool? Okay. Like I said, this is my way of remembering this particular formula. You'll have another way of remembering it yourselves, but the more you use it, the more you will remember it. Good? Okay, so here's the thing. I need to find the sine of pi over 6. Well, pi over 6 is first quadrant, isn't it? And that's a 30-degree angle, isn't it? Okay, guess what? Yep. So let's get our triangle in first quadrant. I'm talking about a 30-degree angle. So that goes at the origin. Here's my 60 degrees. And then I have to label each side of this triangle. And hopefully you've labeled the way I've labeled it. Okay. So the sine of pi over 6, it's still asking me for the sine of 30 degrees. They're the same angle, remember. So the sine of pi over 6, right, is y over r. So in this particular case, we would have 1/2. Agreed? And on the other side of the addition sign, I need that cosine of pi over 6, which is asking for the cosine of 30 degrees, which is square root of 3 over 2, x over r. Good? Okay, so 3 pi over 4. That's the next angle I've got to work with. And you're like, well, which quadrant is that in? Well, here's how it's and for me, this is the easiest way to figure it out. I know pi is here, and that's over 1, isn't it? If I rewrite pi with a denominator of 4, that means pi is equivalent to 4 pi over 4, isn't it? Is 3 pi over 4 less than that or greater than that? Yeah, it's less than that. This is going to be a second quadrant angle. So it's going to go all the way here. This will be 3 pi over 4, which means this distance, that's right, is pi over 4. Which means you are drawing a 45, 45, 90-degree triangle. Because when you got the denominator of 4, that's the 45-degree triangle, right? Okay, so I know it's in second quadrant, so my x value is negative, isn't it? Okay, so the cosine is x over r. Well, you're going to have to rationalize it. So that's negative square root of 2 over 2. And the sine would be positive, and after you rationalize it, you get square root of 2 over 2. Cool? Okay? You have to make certain that you know these particular angles in radian measurement, what they translate to in degrees. Keep those together always, and it helps you draw these two different triangles that you need. And knowing which quadrant these angles are in helps me with the answers being positive or negative. So I multiply the first two fractions together. I multiply the last two fractions together. Both have the same denominator of 4. Yay! But can you add the roots? You're right, you can't. Why not? Because they're not the same. And man, is addition picky. Addition is like things have to be the same to add. So I may not be able to add them, but I can write it like this. I can write it as negative square root of 2 plus square root of 6 over 4. I can write it as one big fraction. And you know, they may even switch it around because some authors of the book don't like the negative being first, so they'll rewrite the order. Regardless, it's the same answer. Cool? Okay, so hang in there. Got another one for us. Okay, so let's look at this next problem. They're asking me to find the cosine of 165 degrees. And so some of you are going, okay, is that a typical angle? Here's how you're going to find out. Let's find out what the reference angle for this is. 165 degrees is in which quadrant? Excellent, quadrant 2. So from 0 degrees, and this is 180 degrees, remember, I'm going into quadrant 2, 165 degrees, aren't I? Good. So now the question is, what's the reference angle? Remember, the reference angle is always off of the x-axis. So from here to here, yeah, that's a 15-degree angle. Is 15 degrees one of our typical angle measurements for reference angles or for any angle? No, it's not. Remember, we spoke about in the last problem in radian measurement, but in degree measurement, it's 30 degrees, 45 degrees, 60 degrees, and 90 degrees. 15 degrees is not one of our typical angle measurements for reference angles, for non-calculator use. Are you all with me? Okay, so hang in there. Okay, so I'm back. So 15 degrees is not a typical angle measurement that we can find without a calculator, which means 165 degrees is not a typical angle that I can find without a calculator. So, and since the directions said find the exact value, that means no calculator, which means I am going to have to break this up into two different angle measurements. And when I do that, I can use the cosine sum or difference formula. Got it? Okay, now there's a number of different combinations that will give you 165 degrees. Mind you, whichever angles you choose need to be one of these or a multiple thereof. So for instance, maybe I could use 60 degrees because that's twice, right? Or let's even do something different. Maybe I can use two 45s, or maybe I need to use three 45s, or maybe I can use two 60s, whatever. Are you with me? So here are some possible combinations that are running through my head. What I'm seeing is if I use two 60-degree angles, that's 120 degrees, right? And all I would need to add is 45 degrees to that to get 165 degrees. So I could use these two angles. Here's another combination. What we could do is we could actually use three 45-degree angles, because that will give me 135 degrees, and add to it 30 degrees, which will still give me 165 degrees. These are only two possibilities. And to be honest with you, it doesn't matter which one I use, I'm going to get the exact same answer. So, do you care which one we use? Okay, so then let's go with the first one. So let's rewrite this. We can rewrite this as the cosine of 120 degrees plus 45 degrees, correct? Which means we have to use our sum and difference formula, don't we? Okay, so what this is going to look like, and I'm going to write it underneath. Remember, cosine's the greedy one. That's how I remember it. Cosine's the greedy one. So this means it's going to be equal to the cosine of 120 degrees times the cosine of 45 degrees. And then it's going to be the sine of 120 degrees times the sine of 45 degrees. And since this was addition, And cosine's the greedy one, it changes to subtraction. Cool? All right. So, you know, we worked with 45 degrees in the last problem, didn't we? And 45 degrees is in quadrant 1, isn't it? So, the cosine and sine of 45 degrees are the exact same measurement. Square root of 2 over 2. So I don't have to do too much work there since I actually found it in the last problem. But what I do have to figure out is the sine of 120 degrees. So I'm going to use, and I'll draw this. I'll draw a new one. Why not? So what I'm going to do is draw my xy axis again. And 120 degrees is in second quadrant, which means its reference angle is 60 degrees, isn't it? So when I draw the triangle, the right triangle, 60 degrees is the reference angle I'm going to be using. And here will be your 30-degree angle. So let's make sure we label it properly. Since we're in quadrant 2, the x is going to be negative. The y will be positive, and the radius, well, radius is always positive, isn't it? Okay, so the cosine of 120 degrees. Remember, 60 degrees is the reference angle for it, so I'm using that in quadrant 2. So the cosine of 120 degrees, cosine is x over r, so that's a negative 1/2. Sine would be y over r, and that will be positive, which, when I start multiplying my fractions, I get negative square root of 2 over 4 minus square root of 6 over 4. Cool? Can I actually subtract these? No, I can't. Even though the denominators are the same, I cannot add or subtract these roots since they are different from each other. Good? Hang in there. Got another example for us. Okay, so let's look at this third problem. So they're asking us to take the tangent of 105 degrees. And some of you already know if this is a typical angle that we can find the tangent of without a calculator, and some of you are not certain. So for those of you who are not certain, let's find its reference angle. 105 degrees is in which quadrant? Excellent, second quadrant. So this is 105 degrees, right? Which means this reference angle would be 75 degrees, wouldn't it? Well, 75 degrees is not a typical reference angle for us. Remember, the typical reference angles are from those triangles and that unit circle. And they are 30 degrees, 45 degrees, 60 degrees, and 90 degrees. 75 degrees isn't it. So 105 degrees is not a typical angle for us, which means, you guessed it, got to do the same thing that we've been doing. So I've got to find two angles that will add or subtract to 105 degrees. Yeah, this one's actually pretty easy, isn't it? Because I see right away that if I take 45 degrees and add it to the 60 degrees, that gives me 105 degrees right away, doesn't it? Good. So let's talk about the distribution. It's not the typical distribution, right? It's the formula. And this formula for tangent almost looks like a distribution problem, if you recall. Let me get this guy out of our way. And now that's where the similarity ends, because we have this funky little denominator that, unless we know where it derived from, we're like, okay, I have to remember the denominator. So 1 minus, since that was addition, the product of these two. Okay. Both of these are first quadrant angles, aren't they? 45 and 60 degrees, correct? So, let me actually hang in there a second, because since they're both first quadrant angles, I don't really need the entire XY grid system. All I need to draw is basically the first quadrant, right? So, I'm talking 45 degrees right? Here's 0 degrees. I draw my triangle. This is 45 degrees up here also. Since it's in first quadrant, x and y are both positive, so I have to label this correctly. There. That's pretty good, isn't it? Okay. Now, tangent is y over x. So 1 over 1 is, good, 1. And now I've got to come up with a 60-degree angle. So gratefully, that's also first quadrant. And remember, since it's 60 degrees, that goes at the origin, which means up here is 30 degrees. And now you've got to know how to label your triangle correctly. Either that or you've memorized these all, and that's great if you have. I haven't. I just know how to draw my triangles very well. So, and x and y are both positive since we're in first quadrant, right? Now remember, I'm talking about tangent, which is y over x. So square root of 3 over 1 is, good, square root of 3. Cool? All right, so it looks like we have 1 plus square root of 3 over 1 minus square root of 3. And you're like, yay, done. That was quick. It was quick, but no, you're not done. Why? You can't leave the square root on the bottom, so you got to rationalize. Ah, lovely. Which means you've got to multiply the denominator by, let's see if you remember the word. It's conjugate. So it's 1 plus square root of 3. And yep, you have to multiply it to the top and bottom. So we are in rationalizing mode. Okay, so let's look at the numerator. We can handle this. 1 times 1. 1 times square root of 3. Square root of 3 times 1. Right? The denominator, 1 times 1. 1 times square root of 3. Negative root 3 times 1. Negative square root of 3 times positive square root of 3. Good, negative 3. Okay, so the numerator, I can add the 1's together and I can add the square root of 3's together, can't I? The denominator, these guys in the middle drop, and I end up with a negative 2, don't I? I can reduce this, can't I? When I reduce it, I end up with negative 1 minus the square root of 3. Cool? Okay, this was the last step you had to make certain to do. You had to rationalize that denominator because unless they say otherwise, you can't leave that square root on the bottom. Good? Okay, so hang in there. No surprise, I got another one for you. Okay, so here we are with 2 more problems. And the directions haven't changed. They want us to find the exact value, but no calculator. So here's the deal. Let's look at number 4. We're like, hey, 30 degrees. That's a typical angle that we can find the sine and cosine of by drawing our triangle, right? But 15 degrees isn't. And no, you can't say 15 degrees is half of 30 and go from there. That just doesn't work that way, trust me. We'll deal with that in another lecture. Okay, here's the deal. I am noticing something on number 4, though. I'm noticing that before the subtraction sign, I have 2 cosines multiplied together. And then after the subtraction sign, I have 2 sines multiplied together with the exact same angles that I had with the cosines. You know what this looks like? This looks like one of the sum and difference formulas already distributed. Which would it be since the cosines come first? Yep, it would be a cosine one because cosine's a greedy one, which means I would be looking at the cosine of, yep, 30 degrees and 15 degrees. And would I be adding them together or subtracting them? Since cosine's the greedy one, the sign it has, which is subtraction here, turns to addition. And so I'm actually looking for the cosine of a 45-degree angle. Now we've done that enough in the last 2 problems. What's the cosine of a 45-degree angle? I heard you. Square root of 2 over 2. You're like, is that it? Yeah, quick and simple, right? Keep it that way. Let's look at number 5. Okay, so do you notice? I have a sine times a cosine, and over here I've got the cosine times the sine of the exact same angles, right? But they're reversed order, so to speak. Sine of this angle and the cosine of the exact same angle on the other side of addition. Cosine of pi over 3, and on the other side of the addition it's sine of pi over 3. Boy, this looks familiar. It looks like, yeah, a trig function already distributed. And which trig function? Excellent, sine. So it looks like I can actually write this as the sine, and I'm going to take 5 pi over 12 and the pi over 3, and what operation would you do between them? Excellent, it would stay addition. Okay, I'm adding fractions. Great, common denominator. So 5 pi over 12 plus 4 pi over 12. Wonderful. Which would give me the sine of 9 pi over 12. And as with all fractions, you reduce if you can. So you're actually taking the sine of 3 pi over 4. Cool? Wow, this looks like another one we did in what, the first problem or something like that? So what's the sine of 3 pi over 4? Yep, square root of 2 over 2. And it's positive, even though this is a second quadrant angle, it's positive because the y is positive in quadrant 2. Good? I got a brain teaser for us, so hang in there. Okay, so here's that brain teaser I mentioned. I'm taking the sine of this thing in the brackets. And it's like, well, what is this thing in the brackets actually representing? Okay, here's the deal. Remember when you see an inverse with a trig function? That means this 9 over 41. Is that the angle or is that the answer? That's the answer, which means this whole thing is representing the, excellent, that whole thing is representing the angle. Over here, in the bracket, I see a cosine with an inverse. So is this negative 3/5 the angle or the answer? That's the answer, which means this also represents an angle, doesn't it? Now, I'm going to tell you right now, I cannot assume these are the exact same angles. Even if this one had a 5 in the denominator, I cannot assume it's the exact same angles. I always assume they're two different angles. Always. Are you with me? So I'm going to call this one alpha, and I'm going to call this one beta, which means I am actually taking the sine, and I'm going to write it over here, the sine of alpha minus beta. Wow, well this looks familiar, doesn't it? That's right. It's one of the sum and difference formulas, isn't it? Which means we are going to have to do that distribution, aren't we? So this means I'm looking for the, since it's the sine of alpha minus beta, we are going to take the sine of alpha and the cosine of beta multiplied. Since it's subtraction, it stays subtraction because sine's not the greedy one. And on the other side, I'm going to take cosine of alpha and sine of beta multiplied together. Cool? Okay, well that's not so bad. But I got to know the sine and cosine of alpha and the sine and cosine of beta. All right, I got some work to do. So I'm going to talk about alpha first. What I know is that alpha equals the sine inverse of 9 over 41. Agreed? Is 41 a typical denominator? Answer? Nope, it's not. Because none of my triangles and the unit circle, none of them have a 41 on it, let alone a 9, which means I'm going to have to draw my own triangle. Got it? So I'm going to put alpha here, and it doesn't matter if you put alpha up top. It doesn't matter. What matters is you label it correctly. So sine is opposite over hypotenuse. So according to this, the opposite side of alpha is 9 and my hypotenuse is 41. And I have got to find this unknown side now, right? So how are you going to find it? That's right, Pythagorean Theorem. So you're going to have 9 squared plus b squared equals 41 squared, right? 81 plus b squared equals, what did I get? 1681. So b squared equals 1600, and b is either equal to a positive 40 or a negative 40. And I know you're going, well, how do I know which one to take? Unless they tell me otherwise, unless they tell me I'm in a certain quadrant, I'm always going to make it positive. So this side is going to be a positive 40. So now question for you. Do I know the sine of alpha? Yeah, opposite over hypotenuse, so 9 over 41, right? Do I know the cosine of alpha? Yeah, adjacent over, right? Good. Now I got to deal with beta. All right, so let's go over here. I've got some more room. So beta, I know beta equals the cosine inverse of negative 3 over 5. Well, just like over there, the 3 and the 5 aren't on any of my two triangles, 45, 45, 90, or 30, 60, 90 degrees, and those numbers aren't even on the unit circle. The unit circles are a bunch of ones and zeros. That's right, draw your own. So I'm going to put beta here. You could have put it up there. This is just my consistency. I always put the angle here. That's just me. And what I do know is cosine is the adjacent over the hypotenuse. So I know my adjacent side is negative 3 and my hypotenuse is 5 because the hypotenuse is always positive. And now, same deal, I've got an unknown side. And how are you going to find it? That's right, Pythagorean Theorem. And I know some of you already found it or you remember this is one of those typical Pythagorean triples. So this side is a 4 and it is going to be positive because they didn't tell me a quadrant, so they ain't getting a negative out of me. Cool? All right, so the cosine of beta, negative 3/5. The sine of beta, 4 over 5. Good? Okay, so let's get to multiplying. Looks like I have a negative 27 over 205 minus 160 over 205, which gives me a negative 187 over 205. And can that be reduced? No. So, this brain teaser actually made you think of what you were really taking the sine of. It was really taking the sine of two separate angles. And I had to figure out what each angle was in order, what each triangle was in order to fill in my cosines and sines up here. Good? Okay, I have one verification problem for us, so hang in there. I'll be right back. Okay, they're asking us to verify this identity. So remember some of the ground rules. One ground rule is you can't move anything from the left to the right. The other ground rule is you can only work one side at a time. So which side do you want to work? Yeah, I want to work with the left side also because there's more stuff I can do. So looking at the left side, what do you see that we can do? Yeah, that numerator looks like a distribution problem, doesn't it? So I am going to take my sine and I'm going to distribute it using one of those formulas, right? So I've got the sine of alpha times the cosine of beta plus cosine of alpha times the sine of beta all over this denominator, right? And that equals that right side. Agreed? Okay, so now I've got this fraction with an addition problem in the numerator. So help me out. This denominator is a multiplication problem, right? So my question to you is this. This denominator, does it belong to both numerators or just one? And if you're like, well, I'm not sure, so let me back you up to a problem that we did a little earlier in this section. So do you remember we ended up with an answer that looked like this? Right? And since the denominators were the same, we could combine them, right? Well, here's the deal. This side is this answer. So if I can go from here to here, then why can't I go backwards and split them back apart? So come on, let's go split them. It looks like I have the sine of alpha and the cosine of beta over this denominator plus the second part of my numerator is the cosine of alpha and the sine of beta over sine of alpha cosine of beta equals the right side. Are you with me? Okay. Now, I'm noticing that I wrote something wrong on the right side. And I'm grateful I caught it now, because if I didn't catch it, things were going to come out a little cattywomp, shall I say. Okay, so gratefully it's easy for me to erase on this light board. Hopefully you were able to erase. So now check it out. This first fraction, the numerator and denominator are exactly the same, aren't they? Yeah, so that's just a 1, isn't it? Now over here, on the numerator I have a multiplication problem. On the denominator I have a multiplication problem, right? So do I have to keep these together, or can I look at them separate? Good, you can look at them separate. So here's how I'm going to look at them. I'm going to look at this as the cosine of alpha over the sine of alpha. Why did I decide to look at those two? Because they both have the same angle, alpha. I'm not looking at the trig function, I'm looking at the fact that they both have the same angle, alpha. And on the other one, I have the sine of beta over the cosine of beta. Again, those two I looked at together because they both have the same angle, beta. And now I'm noticing that I have 1 plus. What's cosine over sine? Yeah, cotangent, as long as the angles are the same. Gratefully they are. Cotangent alpha. What's sine over cosine? Tangent, as long as the angles are the same. And gratefully they are. And so this equals, oh, look at that, 1 plus cotangent of alpha, tangent of beta. Gratefully I caught my writing error. And this checks, and now this is verified. Woohoo! So, I think you know what I'm going to say by now. You have fun with this stuff, and I'll catch you on the flip side.